Talking about Einstein at home, which is a method of getting the public involved in gravitational wave research. And I will, of course, be speaking on behalf of a large team that is working on Einstein at home, headed by Bruce Allen. And if you're interested in getting involved in this, you can just visit our website and start running gravitational wave searches on your computer if you aren't already. So, the summary of my talk is basically that we're interested in looking for gravitational waves from spinning neutron stars. And searching for this particular source of gravitational waves is hard to detect. The detection strategies are computationally limited, which means that basically we get better sensitivity to these waves the more computing power that we throw at the problem. So Einstein at home is a method of addressing this limitation. The idea is that the data analysis gets farmed out to hundreds of thousands of machines in the general public. And these machines will crunch on the data using their spare cycles when they're not doing anything else. And we currently have actually over 50 teraflops of computing power currently working on this problem, which is a pretty good amount. The current status of Einstein at home is that the analysis of LIGO's third science run, S3, is being completed and published on the web. The actual crunching in public of the S4 science run is complete, and we're starting to do the post-processing. And data from the fifth science run is currently being sent out to the machines in the public. So that's the summary. Outline of my talk is I'll start by discussing gravitational waves from neutron stars, why this is the problem that we're addressing. I'll go on to talk about Einstein at home and the underlying software driving it, which is called BOINC. I'll give a timeline of the Einstein at home project. I'll describe the S3 science run search, pulsar search, the methods that we used and the results that we got. Some of the lessons that we drew from that search, particularly in how Einstein at home worked. And then a status report on the S4 and S5 analyses. So, to start out with, what are we looking for? We're looking for gravitational waves from neutron stars. Now, a neutron star, you all know what a neutron star is. It's something about the mass of our sun and about the size of Los Angeles. And they spin, and they will emit gravitational waves if they have any asymmetry in their structure. Basically, anything that causes their gravitational field to change with time will produce a gravitational wave. For LIGO, these will be a continuous gravitational wave source. They typically last for thousands of years. So from the LIGO context, they are always on. They are at a very nearly constant frequency, where the gravitational wave frequency is up to a kilohertz or more, maybe one or 2 kilohertz. They're almost constant frequency, but they are modulated, both from the star itself, maybe spinning down or maybe accelerated, but also the detector is sitting on the Earth is spinning, the Earth is going around the sun. That produces a Doppler shift in the signal. So to search for these signals, we need to demodulate these small variations in the frequency. Now, the signal to noise of the signal that we're looking for basically increases the longer that we look at the source. It grows roughly as the square root of the number of cycles of waveform that we can integrate over. However, the computational cost of doing the demodulation, we have to demodulate it each different position in the sky, each different intrinsic spin down, and each particular frequency of the source is a separate sort of demodulation that we need to apply to the signal, that we need to look for. So the actual computational cost of the search grows as, again, some power of the number of cycles. Actually, as the number of cycles raised to the power of the number of search parameters plus 1. So in our case, say we're searching for waves of various frequencies coming from possible regions in the sky. Roughly speaking, we'll get a computational cost for the search that grows as the fourth power of the number of cycles. So from this, you can see that although we would like to observe for as long as possible, our computational cost is rising much more rapidly in time than our computing resources. And so our searches are going to be computationally limited. We can only, with our computing resources, we can only search a certain length of template and only get a certain level of signal to noise from that. So we would like to get as much computational power as possible. And that's where Einstein at home comes in. Einstein at home has the science goal of distributing this computational work to computers in the general public. And we're aiming at detection of gravitational waves from pulsars. At present, we're not looking at doing upper limit analyses with Einstein at home. This distribution of work is accomplished using a framework called the Berkeley Open Infrastructure for Network Computing, or BOINC, which is a system for distributing work that was originally developed at Berkeley for the SETI at home, the search for extraterrestrial intelligence. Einstein at home is more than just a science project. It's also an outreach project aimed at getting the public interested in gravitational wave research. It was launched at the AAAS meeting on February 19th, 2005. It is a cornerstone, or at least was a cornerstone, of the American Physical Society World Year of Physics 2005 outreach activities. It currently has over 100,000 registered users, of which about 50,000 are actually active, from over 180 countries, and they currently contribute something like 50 teraflops of computing power to our search. There are many science projects that use BOINC. Of them, Einstein at home is currently the second most popular BOINC project after searching for extraterrestrial intelligences, the original BOINC project. Yes?
Can you just name what some of these other projects are, third, fourth, fifth place?
I think this third place is climate prediction, the BBC climate prediction search. Which there's Rosetta at home, which is a protein folding, I think. No, there's protein folding at home. Rosetta at home is another protein. Again, I haven't looked into it, but modeling proteins, searching for pharmaceutical cures. Perhaps much more useful stuff than Einstein at home, but perhaps doesn't catch the public imagination to the same degree. So I'll just show this picture of the growth of Einstein at home over time. Started in early 2005 and has been growing fairly steadily throughout. Now has about 120,000 users registered to the project. And it truly is a global endeavor. These people, the users who are contributing their computers are found in every developed nation in the world and most of the developing nations as well, with only a few exceptions that haven't yet contributed. So I'm mentioning BOINC. Let's describe a bit how it works. So the heart of a BOINC project is basically a database which keeps track of work that needs to be done, results that have come back, lists of users and the hosts that they have, and fora or discussion groups for communicating with the users and letting them talk amongst themselves. This database communicates to the outside world through a web server, which hosts the web pages for the project and also handles uploads and downloads. Then, through the internet, we connect to the various clients, the various users who are contributing to the project. All communications are initiated by the clients. The users download a BOINC client, a program or process that runs on their machines. And they choose one or more BOINC projects that they would like to contribute to. The BOINC client process then contacts the web server and downloads and installs the analysis applications for whatever search they're doing. So in our case, an application that's called Einstein. So it'll download the application, it'll download work to be done, and start working away. When it finishes a result, it uploads it, contacts the server to upload it. And at that time, it'll receive more work, and it can also receive an updated application. So if we want to change the kind of search we're doing, if we want to search for something other than pulsars, if we want to search for inspirals or extreme mass ratio inspirals for LISO or something, they wouldn't have to explicitly install a new program, a new search program. We would just make the new application available, and their BOINC client would install it automatically. On the server side, there are also various other daemons and processes that handle the data. There are generic BOINC daemons which handle the transitioner, which handles sending out work units and seeing what works need to be done. Deleters and purgers, which remove information from the database when it's no longer needed. Also, project-specific daemons. A generator, which generates new work to be done. A validator, which checks the validity of the returned results. And an assimilator, which takes the results and creates sort of a scientific database of them. So, actually, I will give you a little, for those of you who weren't here, I will give you a little shot of the screensaver. This is the screensaver that runs. It shows a picture of the sky. This little orange crosshairs here is the current point on the sky that the user, in this case me, is currently demodulating. These are locations of known pulsars and in purple and supernova remnants in brown. We also have the locations of the Hanford Livingston, and GEO detectors marked on the map. So let's give a timeline of how for Einstein at Home. So development of Einstein at Home began in the spring of 2004. By November 2004, it was ready for testing, an unofficial test launch on a small group of users. It was officially public launched on 19th of February 2005, analyzing S3 data. On May, we started the second search of the S3 data using the final calibrations and final cleaning of the data. And that's the search that I'll be discussing later. It started a preliminary search of S4 data in June 2005. By September, we had published partial S3 results on the website. December, we started an improved S4 search, making several optimizations and improvements. And just 2 weeks ago, the last of the S4 data from that improved search was sent out, and we started sending out S5 data. So where do we stand now? This is a snapshot of the server status page that I downloaded a week ago when I was writing this talk. You see that we have over 70,000 nodes that are active. We're actively working on the Einstein at Home project. They have a total benchmark speed of over 100 teraflops, of which we are currently of which they're currently contributing 50 teraflops to Einstein at Home. At this rate, the current S5 search is expected to last about a year, but we expect it to go faster. We're going to make available faster applications that should be able to crunch the data faster, and we are expecting probably our user base will grow and they'll start bringing in faster computers along with them.
When you say the S5 search, you talk about the first effort through the commissioning, or the entire thing up till now, or?
I think it's the entire thing up till now, but I'm not sure. So I'll just give an update. Last I checked today, the actual speed that of data processing that we're getting is over 70 teraflops increased in the last week. But part of that, I think, is due to the SETI at Home being is shut down for some reason. So we may be just be getting a bump from that. So let's talk about the S3 search, going back to the one that we actually have results for. This was a search of the most sensitive 600 hours of Hanford 4-kilometer interferometer data over a range of frequencies from 50 to 1500 hertz. So the data was calibrated to produce basically strain as a function of time. That was bandpassed into the frequency band of interest, and it was windowed into 30-minute segments, which were then FFT'd. This is the basic data product that we start with, these short Fourier transforms. These were then cleaned of all known instrumental lines. So basically frequency bands where there was a clear line of a known instrumental source, such as a violin mode, a thermal resonance of one of the test masses, things like that. Things where we had a good model of what the source of the contamination was. These were then divided into overlapping half-hertz bands, the narrow-banded SFTs, and collected into 10-hour stretches. So we would have a half-hertz band that consists of basically 20 narrow-banded short Fourier transforms spanning a 10-hour stretch. From that, we compute what's called the F statistic, a coherent frequency domain optimal statistic for a source with a modeled with a particularly modeled phase modulation. This is described in a paper by Jarnowski et al., 1998. It's the standard statistic that we use for the frequency domain searches for pulsars. The search was done over an isotropic sky grid of 31,000 different points in the sky, no searching over pulsar spin down. So basically just sky position and frequency are the search parameters. For each sky position and frequency, we select candidates which have basically a chi-squared parameter that is greater than 25 in a given 10-hour stretch. These are the candidates. These candidates are considered coincident if they occur in 2 or more of these 10-hour stretches within a millihertz of one another and within 0.02 radians on the sky. So then, basically, for each sky position and frequency, we count the number of such coincident candidates, which will be a number less than less than or equal to 60 because we're looking at a 600-hour stretch of data and looking for coincidences among 10-hour substretches. 10 hours, by the way, was chosen basically based on what we expected our computational costs would be. That was sort of the largest length of data that we could coherently analyze with in the required time with the computational resources we were expecting. So the implementation of this is that we send out to each host a particular half-hertz band with all 60 10-hour stretches in that band, which forms a file with a size of about 14 megabytes. The host is then assigned a work unit, or a particular part of that data set, to search. It searches a 0.1 hertz subband over all sky positions for 2 of the 60 10-hour stretches. And this is chosen so that the average time to complete a work unit is about 12 hours for the typical host that we had at the time. The host then returns a list of all candidates that are coincident in both of the 10-hour stretches that it's been assigned. This was a step that was added to reduce the flood of data back from each host. By requiring them to do a first-level coincidence search, we could reduce the size of the uploads to something on the order of 100 kilobytes. And since we don't have control over the hosts, they may not necessarily be as reliable as a cluster that we maintain ourselves. People may overclock their hosts to get better performance. People may cheat to try and get credit without doing work. So each work unit, the results from each work unit, are compared among 3 different hosts. We send the same work unit out to 3 separate hosts and compare the results that come back. And only if they agree do we grant them credit and put the result into our database. So that's the method. That's how the search was done. So what are the results that we get back? And basically, the result that we get back is a number of coincidences as a function of 3 search parameters: the right ascension and declination on the sky, that's standard astronomical coordinates, and the frequency. So we basically have blobs in a box representing the number of coincidences for each sky position and frequency. Now, in the pictures that I give you, we're basically going to project that box into one of 2 different planes, either looking at the right ascension declination, or the plane of sky positions, or frequency and declination, to basically give you a sense of the spectrum of these things, and we'll display the peak value of the number of coincidences projected onto these 2 planes. So here's an actual result for a typical clean band of data, a band that has no instrumental artifacts. Basically looks like Gaussian noise. So this is a particular band from 300 to 325 hertz. Over all the sky, it looks pretty clean. The number of coincidences is typically less than or equal to 6, which is roughly what one expects from Gaussian noise. So to test that we could actually see something, put in simulated signals, software injections. We inject into the data a signal from a simulated pulsar. This is one with a gravitational wave strain of around 6 × 10 to the minus 23 at this sky location, at this frequency, and we see it shows up quite clearly in the data. It gets smeared out a bit because the total observation time is only 12 months. Our ability to resolve things on the sky is not perfect, so it gets smeared out, and I'll discuss that a bit later. We also, in order to test the integrity of the pipeline, there were also hardware injections put into the data by actually jiggling the masses in LIGO in the manner that a pulsar signal would generate. And we see that these hardware injections, again, from something around 10 to the minus 23 strain, were clearly visible, although they were smeared out a bit more. And this is probably due to the fact that hardware injections were only on between 1/3 and 2/3 of the time, so they have even poorer sky resolution. And here is an example of instrumental artifacts, violin modes, and other artifacts in the instrument that have constant frequency. These artifacts get smeared into a characteristic band across the sky. So they can be identified to some degree by that. And I'll explain why they get smeared in that way. To understand that, you need to understand a bit about how the demodulation is done. A putative pulsar signal is not necessarily a constant frequency signal, but is going to be Doppler modulated. Basically, frequency is a function of time, is its intrinsic frequency modulated by the motion of the detector towards or away from the source. Now, this is the dominant motion of the detector is actually the orbital motion of the Earth. There's also the rotation of the Earth, but that's a much smaller velocity. The orbital motion of the Earth is about 100 times greater. Now, over a short enough time, we're not traveling very far around the orbit of the Earth. Over 2 months, we're basically just moving along a small arc. So basically, we have what is effectively a constant acceleration towards the sun that is dominating the time dependence of the frequency. So we have a constant offset to the frequency plus a time-dependent modulation of the frequency that depends only on the acceleration of the Earth. This means that there is a band on the sky where the acceleration in the direction of the source is very nearly zero. And that means that the signal from this putative pulsar would be very nearly constant in frequency. Now, the detector has many things that could cause a constant frequency signal. Basically, any repeating signal that is not somehow synchronized to the Earth's orbital motion will look, for our purposes, like a constant frequency contaminant. And these contaminants will basically mimic a pulsar signal from one of these bad directions. Now, and so that's why we see contamination in certain specific frequency bands in certain specific sky directions. Now, for the future, longer observations over many months will tend to reduce this effect. This band will get spread out more. And basically, over a year, there would be no preferred direction in the sky except directly above and below the plane of the Earth's orbit. Those will always probably be relatively bad directions where we will be less sensitive to pulsars because we won't be able to distinguish them from instrumental artifacts. So, given those issues, here are the final results from S3. With the various injections, we see we have the band of artifacts plus particular artifacts that we threw in ourselves. Without injections, it looks a lot cleaner. We just have basically this band of instrumental artifacts in the sky. And as I say, most of the significant events were either the injections that we put in or were in this particular bad band. There were a few outliers, not highly statistically significant, not very high levels of significance, but still perhaps more than we would expect from Gaussian noise alone. So the way we characterize these is split the data into 0.1 hertz bands. If we do that, only 67 frequency bands out of the entire range of frequencies contained candidates with more than 10 coincidences. And of those, 59 lie within the band where the acceleration in the acceleration dotted into the sky position is 0 for at least part of the instrument, or for at least part of the run. So those we basically rule those out as being indistinguishable from instrumental artifacts. Of the remaining 8 candidates, some were later identified as specific instrumental artifacts that were on for short periods of time. Others, while not necessarily in this particular band, were sufficiently near it that we thought that they're likely to be smeared out things in that band that had gotten sort of scattered or smeared out of it. All of these 8 candidates were much lower significance than a lot of than most of the other things that were in the instrument band. They are all relatively low significance. But most importantly, none of these showed up in a follow-up search of the S4 data. So we conclude that there was no evidence of a pulsar signal found at the level of sensitivity that we had for the S3 science run. So that's the result. That's the result of the scientific analysis from S3. But what are some of the lessons that we took from the use of Einstein at home? Well, one is a cost-benefit analysis. It took about 8 months to set up the our Einstein at home servers and to convert the analysis code to run within the BOINC framework. And we feel it was definitely worth it. For that 8 months investment, we get a reasonably reliable cluster of over 50,000 nodes working on our problem, and one that is constantly being upgraded with the latest hardware at no significant cost to us. Another lesson, though, from Einstein at home is that the sociology of the problem is important. You can't just focus on the science. You also have to consider sociological aspects when setting up the project, when promoting it, when communicating with the users. Basically, these people are volunteering their time, and they need to feel like this is worthwhile to them, that it's something useful. So it's important to have an interesting website that the users can identify with. We have user profiles. We have a user of the day. There is a certain amount of competitiveness. There's lists of of the top-ranked users in terms of the work that they're contributing. There are various fora, discussion groups for users to communicate with us and with each other. And these discussion groups are not limited to science. There's an open discussion group where they talk about everything from politics to the weather or anything else, basically trying to create an online community of people who have certain shared interests. We also felt it was important to present the results of the S3 analysis on the website in a manner that was accessible to the users so that they would see the fruits of their labor. Now, one aspect of this sociology that I've mentioned is the ultimate source of user motivation, at least for some users, the BOINC credit, which is just a measure of the cumulative instructions, floating point operations, that a user's computers have contributed to the project. Now, since the BOINC framework allows users to contribute to many different projects, so they spread their computing resources among many projects, they will tend to migrate to projects that give them the best return. Basically, if a project is perceived as being stingy with its credits, that a given amount of computing time doesn't seem to yield the same amount of credits as they get from another project, they will migrate to the one that gives them the best return. Users will appreciate having optimized applications that make their computer run a little bit faster than the average computer. So they get a little bit more credit from the time that they invest on their computer than people who don't have those optimized applications. And another thing might sound surprising, but perhaps shouldn't be, is that users will in fact cheat for credit. They will return garbage results and claim the credit for that work unit even though they didn't do the work for it. And this turned out to be the main reason for keeping our triple redundant validation procedure. If it weren't for this, if the only reason for invalid results were that there were occasional glitches or memory errors or cosmic rays or something, that would only affect a few results in like a fraction of a percent of the results, we might be willing to tolerate that. A fraction of a percent of the results would be garbage. We would either not see something that was there, but those would be small blind spots, or we might get a false event which we would then discard through follow-up studies. But if it were known that we were not actually checking the results that came back, then that people could get away with just sending back garbage and claiming the credit, then that would poison the entire atmosphere of the project. People wouldn't feel like they were contributing anything of use. So that turned out to be a main reason for keeping our validation scheme. So now let's go on to the status reports of the searches that are currently underway. For the search of the S4, fourth science run data, certain changes were made. We increased the segment length to 30 hours rather than 10 hours. This was chosen as an optimal figure that would give the best sensitivity for our computational resources, building on the experience we had of how long it would take to complete work units. We added one spin down parameter to the search. Basically, we added a search over the first derivative of frequency, as well as over frequency and sky position. And we search over a range of spin downs that would detect pulsars whose age, as measured by f over f dot, was greater than about 10,000 years. So we wouldn't get very young pulsars that were spinning down very rapidly, but we would get a good number. We used a better grid on the sky, not an isotropic grid, but one that was determined by the overlap of nearby signals. So we could make the grid much finer in regions where higher resolution is required, coarser in regions where the signal was not so well constrained. So we can basically get the best possible number of points on the sky. In this case, each host searches only one 30-hour stretch. A given work unit consists of only one 30-hour stretch. There's no coincidence stage performed at the host end. Instead, the host uses a floating threshold and returns the top 13,000 candidates, regardless of the particular f-statistic value that these are. This gives us better resolution or better sensitivity in places where we have good data, but we don't get flooded with spurious results in places where the data is bad. Also, each host that searches a variable bandwidth of frequency range that goes as f to the minus third, which basically means that each work unit is approximately the same amount of computing time, about 8 hours on average. The status of this search is that the analysis by the hosts took about 6 months. The last work units were sent out 2 weeks ago. And so we're at the stage where we're ready to start our post-processing of the results and getting some scientific results from it. Now, when S4 ends, when the S4 search ends, the S5 begins, so we've started sending out S5 data. The changes that we've made for the S5 search is that we have two types of work units. We have some low-frequency work units in the 50 to 400 hertz range, which process very quickly. And we have work units for the high-frequency range, which process much more slowly. And the BOINC framework has the capability to preferentially send out slower work units, the ones that take more work, and send them to faster hosts. So instead of just maintaining an average time to complete a work unit, we can actually tune it so that we won't have people with slow machines taking a week to send back results. Another change is in the manner that we grant credit. In the past, we granted credit based on the claimed credit from the host. Basically, they would do the work, they would compute how much computational cost it had cost them, and that would be the credit that they would claim. And with 3 results coming back, we would grant the median of the 3 claimed credits to all 3 of them. That way, if someone cheated and was claiming an absurdly large amount of credit, then that would get discarded, and we would pick one of the other 2. Now, as we've gotten more experience with the actual costs of these searches and how long they take, we've gotten to the point where we feel comfortable estimating the credit or the computational cost of each work unit on our end. So we will, with each work unit, we will send out, it'll also have an estimated computational cost, which is the basis for credit. This will reduce the opportunities for people to claim fraudulent credit and will allow us to reduce the redundancy that we need. So we're going to doubly redundant rather than triply redundant. We'll get back a result, compare it against one other result, and only if they disagree will we send it out to a third one to see if we can get a quorum of valid results. The status of this search is, as I said, we started sending out work units 2 weeks ago. It's estimated to take around 6 to 12 months. But I should also mention that our server side has spare capacity. We had previously been holding off recruiting new users because we weren't certain if we were going to overload our server. Now we think we've got enough spare capacity that it's time for us to go out and start recruiting more users. So that's all I have to say. Thank you.